Welcome you all for this video. In this video, we see about converting into a canonical form in the second order partial differential equations. We know about the differential equation. In particular, the partial differential equations means are mathematical equations that describes how quantities change with respect to multiple independent variables, typically time and space. These equations involves partial derivatives of an unknown function with respect to these independent variables. When we consider the key aspects of PDE involves two or more independent variables, which can be spatial coordinates x, y, z, or time t. The dependent variable is an unknown function to its partial derivatives with respect to the independent variables. Partial derivatives means a PDE which includes partial derivatives, which represents the rate of change of the dependent variable with respect to the specific independent variable while keeping the others constant. Partial differential equations are fundamental in various fields including physics, like modeling phenomena in heat transfer, fluid dynamics, and wave propagation. Also, it is used in engineering and finance. Now, we see about the second order partial differential equations. So, consider the equation AUXX plus BUXY plus CUYY plus DUX plus EUY plus FU plus G equal to 0. Now, we change this equation 1 into a canonical form by introducing the new variables psi and eta. Now, the coordinates x and y, Cartesian coordinates, are changed into the canonical terms psi and eta. After introducing that variables in the equation 1, we finally get the equation A tilde u psi psi plus B tilde u psi eta plus C tilde u eta eta plus D tilde u psi plus E tilde u eta plus Fu equal to G. In the equation 1, A, B, C, D, E, F, G are all constants sometimes, or these are sometimes in the way these are sometimes these of the independent variables. Now we see A tilde, B tilde, C tilde, D tilde, and E tilde, and the values are denoted here. By using these values in the equation, we have the canonical equation. In general, we see that the three types of PDEs, hyperbolic, parabolic, and elliptic PDEs. And these are classified accordingly by using the discriminant b square minus 4ac. If b square minus 4ac is greater than 0, then that kind of equation is hyperbolic. If b square minus 4ac equal to 0, then that can be considered as parabolic. And if it is elliptic, then b square minus 4ac is less than 0. So after considering these classification, we will change the corresponding equation into a canonical form. From the physical point of view, these PDs respectively represents the wave propagation, the time-dependent diffusion process, and the steady state or equilibrium process. Thus, hyperbolic equations model the transport of some physical quantity such as fluids or waves. Parabolic problems describe evolutionary phenomena that lead to a steady state described by an elliptic equation. Any elliptic equations are associated to a spatial state of the system, in principle corresponding to the minimum of the energy. Mathematically, the classification of the second order PDE is based upon the possibility of the reducing equation, the given equation, by coordinate transformation to canonical form at a point. So after changing that into a canonical form, we have the equation in terms of psi and eta. Now, let us see one example related to the equation uxx plus secants hyperbolic power x uyy equal to 0. Here, uxx represents dou square u by dou x square, uyy represents dou square u by dou y square. The general form is, as we see in the slide, AUXX plus BUXY plus CUYY plus DUX plus EUY plus FU equal to G. Now, by comparing this equation into the given equation, we have the coefficient uxx is 1, so a equal to 1. And we don't have the coefficient of uxy, so we have b equal to 0. And the coefficient of uyy is secant h power 4yx, so c equal to secant hyperbolic power x, or 4 into x. And the other terms d, e, f, and g are all 0. Now, we find the discriminant b square minus 4ac, and which can be seen that it is minus 4 into secant h power 4x, and we can see that which is always less than 0 except at x equal to 0. So it is an elliptic equation everywhere except at x equal to 0. So we find that the classification, that is the given equation, is elliptic except at x equal to 0 by make use of the discriminant b square minus 4ac equal to 0. Sorry, b square minus 4ac is less than 0. Now we consider the characteristic equation, and the characteristic equation is found by the formula dy by dx equal to b plus or minus root of b square minus 4ac divided by 2a. By using these values given in the equation 1, we have that dy by dx equal to plus or minus secant h square x into I. So we have the complex imaginary value, and dy by dx equal to plus secant h power 2xi means we have dy equal to I into secant h power 2x dx. Finally, we have y equal to I tan h x plus c1 after integrating. So here c1 represents the integrating constant. Similarly, we can find the dy by dx, uh, we can take the dy by dx for negative value, and we obtain y equal to minus I into tan hx plus c2. Here c2 is also an integrating constant. So the characteristic, from the characteristic equations, we found the two constant values c1 and c2, and which can be found as c1 equal to y minus I into tan hx, c2 equal to y plus I into tan hx. Now, let us consider these two constants as psi and eta. So, psi equal to y plus I tan hx, and eta equal to y minus I tan hx. Now, we see psi and eta contains the imaginary part. So for removing that, we introduce again a new two variables, alpha and beta, and which can be defined as alpha equal to 1 by 2 into psi plus eta, and beta equal to 1 by 2i into psi minus eta. So alpha equal to 1 by 2 psi plus eta. So psi plus psi value is y plus I tan h of x minus plus y minus I tan h of x. So we have y, alpha equal to y. After simplification, we get alpha equal to y. And similarly, we get beta equal to tan hx. Now, differentiating alpha with respect to x, we have alpha x equal to 0, so that alpha xx equal to 0. Differentiating alpha with respect to y, we have alpha y equal to 1 and alpha yy equal to 0. Now, differentiating alpha x with respect to y, we have 0. Similarly, if we differentiate beta with respect to x, we have secant h square x, and beta xx, we have 2 secant hyperbolic square x into tan hyperbolic x. And beta xy is 0, beta y equal to 0, and so beta yy is also 0. Now, it is given that the PD is elliptic. Therefore, in general, if it is in the elliptic, then A star, C star are equal and B star equal to 0. Also, we know that the coefficient of A star value, that is A star equal to A alpha x square plus B alpha x alpha y plus C alpha y square. So after substituting these values, we get A star equal to secant hyperbolic power 4 x, and which is also C star. So we have A star equal to C star equal to secant h power 4x. Again, we have the formula for D star, which is A alpha xx plus B alpha xy plus C alpha yy plus D alpha x plus E alpha y. Now, after substituting the values of the partial derivatives in D star, we have it is 0. Similarly, if we take the E star formula and substituting the values of beta xx, beta xy, beta yy, beta x, and beta y, we have E star value as 2 secant h is power 2x into tan hx. And we can say that f star equal to f equal to 0, g star equal to g equal to 0. Now, the transformation of canonical form is A star u alpha alpha plus B star u alpha beta plus C star u beta beta plus D star u alpha plus E star u beta plus F star u equal to G star u, G star. So, we will substitute these values in the equation 5, and then we get secant h power 4x u alpha alpha plus secant h power 4x u beta beta plus 2 secant h power 2x u beta into tan hx equal to 0. So after simplification, we get u alpha alpha plus u beta beta equal to minus 2 tan hx by secant h square x into u beta. Now, if we take beta equal to tan hx, then secant h square x can be written as 1 minus tan h square x. So, we write that as 1 minus beta square. So, we have to change all coordinates in terms of alpha and beta. So, we have to make use of the variables alpha and beta in the obtained equation, and we have to get the equation only in terms of alpha and beta. So here we have changed the tan hx and secant h square x in terms of beta, and finally we obtain the equation, canonical equation is u alpha alpha plus u beta beta equal to minus 2 beta divided by 1 minus beta square into u beta. Now, if we consider modulus of beta is less than 1, then u alpha alpha plus u beta beta equal to 2 beta divided by 1 minus beta square into u beta. So, this is our obtained canonical equation of the equation 1, that is uxx plus secant h power 4x uyy equal to 0. So this is the way of converting the given equation into a canonical form. So here first we have to take the general second order PDE equation 2. Then we have to see the characteristic equation. After seeing that characteristic equation, if it has imaginary part, Then we have to change the two variables alpha and beta, sorry, psi and eta in terms of the variables alpha and beta. Suppose if we don't have the imaginary part in the characteristic equation, then we can directly take psi and eta and we obtain the canonical form in terms of psi and eta. So this is the way of converting the given equation into a canonical form. Then we consider the second order general PDE. Thank you all.